Hello, I use Python for solving this challenge, and first what I did was converting all the features with date like confidential release date, spot date, surface abandon date, and release date to 0 and 1s, 0 for null and 1 for the rows that have a date. And by exploring the surface abandon date, it was obvious that most of the rows with surface abandon date have been abandoned, so I think that was a good predictor. So then I used the Lahi class feature and changed and group some of the values to a bigger group like development or wildcat and things. And also for the well type standardized, I did the same because there was a lot of unique values in these columns, and for the model it was not easy to deal with all these values. It was caused a lot of features for the model to deal with. So for the fracture stages, I just filled in not the numbers, and I used Pearson correlation to find the correlation between the predictors and the target, and it was obvious that the surface abandon date has minus 0.6 correlation with the status code, and also the release date has 0.22, and another one was current operation ID, which has 0.37 correlation with the status code. So these were the features with a large correlation, high correlation with the target, and also for the taking into consideration the dog leg severity and the horizontal leg length, I divided MD feature by the TVD to get a new feature like MD over TVD, and the higher the MD over TVD shows that we have a longer horizontal length or high inclination or azimuth. Maybe we can understand from that. So these are the features that I have used for my classification algorithm or model. And this I first one had encoding for the categorical features, and then use this EPA set ID as the index, and then the feature scaling, and then I ran different models like random forest, which was the best model for me. This is the confusion matrix, and I got 88% F1 score for the train model, and for the validation I got 82%. So 82% F1 score from the random forest. For the logistic regression, the numbers was lower for about 74%, and decision tree also gives 88%, 82%, something similar to the random forest. And for the naive based, I got very low number, 57. And also I used light GBM. I got high numbers like 82%. So for the regression, as the number of rows in the Viking file was smaller than the training, I do a merge and I do imputing and change with not the numbers in the oil and gas and water with zeros and other things. So I plot histograms for the data file and do the same grouping for the live class and things. And I used 3 different models for each of the oil, gas, and water production. There's different parameters for that. So I do some data cleaning and do one-hot encoding and things, and then I fit multiple linear regression, which this is the R squared and mean absolute errors that I get for training, and I run it for all the third models. Also I do stepwise regression to just adjust the R square and compare them to see which ones are not increasing adjusted R-square. So I fit polynomial regression model, also fitting decision tree model, which I got better results, higher R-square, as you can see. Some of the minus R. So, and the random forest regression. So and this is